Hello everybody, it's me back again for day 2 of series. Today we are going to look at what happens when looking at a partial sum doesn't tell us what we want to know about a series. Again, if the partial sums approach a limit, we know we have convergence, but we can't always see that limit by just looking at a couple partial sums. So today we're going to start talking about what you do when you can't just use a partial sum. The first thing you do is you test to see if it is your best friend and mine a geometric series. Okay, a geometric series is the best series you could ever possibly get, and here's why. Number one, they're super easy to recognize. A geometric series is any series that's created by repeated multiplication. Okay, so in other words, if I had the series 1 plus 2 plus 4 plus 8 and so on and so forth, here I have repeated multiplication by 2. Therefore, I would say this has a common ratio of 2. Okay. Conversely, if I had something like 1 minus 1/2 plus 1/4 minus 1/8 and so on and so forth, if you look at these terms, that's repeated multiplication, but in this case, it's repeated multiplication by -1/2. I don't care if the number's positive or negative. If your series is developed by repeated multiplication, it is a geometric series. The only thing you need to know about a geometric series to know if it converges or diverges is the common ratio. And that's usually pretty easy to recognize. If you divide out 2 consecutive terms, you have your common ratio. Okay. So all you need to know about your common ratio, and I think you can do this, is whether or not its absolute value is bigger or smaller than 1. Okay, so there's 2 possibilities for your common ratio. Either the absolute value of it is less than 1, or the absolute value of it is greater than or equal to 1. Okay, now think about what happens if your thing you're multiplying by, your common ratio, is greater than or equal to 1. If it's 1, your terms are going to stay the same. If it's greater than 1, your terms are going to get bigger. If that is the case, you have divergence. Period, end of story. So this series right here, common ratio greater than 1, diverges. See ya, bye, done. Okay. If the common ratio is less than 1, absolute value is less than 1. So again, up here, it's -1/2, fine. If it was -2, that would be divergence. -1/2, so the absolute value of -1/2 is less than 1. We're good to go. That's convergence. And get this, I know what it converges to. No adding up partial sums, none of that business. All I have to do is use this handy dandy formula right here. Okay. A is your first term, if I can spell first. R is your common ratio. So over here in this series, if I want to do A over 1 minus R, my first term is 1. My R value is -1/2. So 1 over 1 plus, since the R is -1/2. So I get 1 over 3/2 or 2/3. In other words, if you start adding these terms up, 1 minus 1/2, you're going to be at 0.5. Then this takes you to 0.75. This is going to bring you back down. The next one's going to bring you back up. And what you're going to see in this series is like, here's the line 2/3. You're going to see your partial sums doing this, kind of bouncing around, but getting closer and closer and closer to 2/3. Okay. Because there's this magic interval from -1 to 1 where geometric series converge, we call that those numbers, the numbers from -1 to 1, the interval of convergence for any geometric series. And we're going to talk in a minute, that becomes a lot more important when the series is made up of not just numbers, but that's to come. Okay, let's take a look at a couple geometric series. All right. We actually just did this one because I'm a genius. I saw it coming. All right, this one, let's take a look. You write out the first couple terms. I always write out the first couple terms. Put a 1 in, this is going to become a 0. So you have 3 times 1/2 to the 0, also known as 3. Okay. Plus, put a 2 in, you have 3 times 1/2, 3/2. put a 3 in. You have 3 times 1/2 squared, also known as 3/4, and so on and so forth. So if you didn't recognize it from its form, that it's going to be repeated multiplication, you should notice it when you start writing out the terms. All you're doing is multiplying by the denominator by 2 every time. That's multiplication by 1/2. Again, when you see an exponential, you already know that is repeated addition or repeated multiplication. By definition, exponentials are repeated multiplication. So as soon as you see a series written in this form, notice down here, exponential, exponential. You've got a geometric series. So first term is 3. And my common ratio here is 1/2. Because my absolute value is less than 1, I know it converges. So I go 3 over 1 minus 1/2. So 3 over 1/2, also known as 6. Okay, so that series is going to converge to 6. Okay, we already know this one converges to 2/3. Let's take a look at this one. Again, if we write out our first few terms, 3/5 to the 0 is 1. 3/5 to the first, 3/5 to the second power, or 9/25. 3/5 to the third power, 27 1/25. Again, I don't actually need to write these out to know this is geometric. My first term is 1. My common ratio is 3/5. So it's going to converge, and it's going to converge to 1 over 1 minus 3/5. So 5 over 2, right? 1 over 2/5 or 5/2. Okay. Number 4 is another geometric. Again, they were a little bit tricky this time. They didn't write the rule for us, but hopefully you can see what's happening here. It's multiplying by pi over 2 every time. So this is a pi over 2 to the n. The only difference is here the n starts at 1. So your first term is pi over 2. Your second term is that squared, then cubed, then to the 4th, to the 5th. This is a geometric series, but hopefully you realize, despite this being a fraction, that it is greater than 1. So this diverges. AP likes to throw geometric series at us where there's a fraction, but the fraction is greater than 1. And I think it's because people glance at a fraction and they're like, oh, it's a fraction, it's less than 1. Be really careful with that. If the fraction, you can multiply by a fraction all day. If it's an improper fraction, it's going to be greater than 1, and that's divergence. Okay, so what we really want to do, because we're big kids, is start looking at series that aren't just made of numbers, that have x's in them. Okay, so this is what we're really talking about when we talk about a power series. So notice this series. It looks rather horrifying for your first series, right? It starts with a 1, and then out of nowhere, x's. So what we have here is an infinitely long polynomial, right? We have every power of x. But with our keen geometric series I, we might notice that what we also have is a geometric series. I have a first term of 1, and I have an r value of x. To get from one term to the next, all I'm doing each time is multiplying by x. So if I have an a value of 1 and an r value of x, I've got myself an infinite series here. That's all the powers of x, and it converges not to a number, but to a function. If I use a over 1 minus r, I get a function. So what we're saying here is that as you start adding more and more and more terms to this polynomial, it starts behaving more and more and more like this rational function. Now, in my humble opinion, this is hands down the coolest part of calculus. So brace yourself. I freaking love this. Okay, check this out. Okay, that series is converging to a function. So what that means, again, is that in its infinite form, this series would exactly match this function. Now, it's not always going to match that function. And this is where interval of convergence comes in. Okay, this series is good. In other words, it converges as long as r is less than 1. Right? So if I choose an x value of 0.5, that series is going to converge. If I choose an x value of 5, that series is not going to converge. And so what we see is an infinitely long polynomial that will nicely mimic this function, but only on a certain interval, only on the interval where this series is going to converge. That interval is called the interval of convergence. So in this case, because I'm multiplying by x every time, the x value has to be between -1 and 1. We call that the interval of convergence. I want to show you what this looks like. Okay, here's the function 1 over 1 minus x. Here come our partial sums. There's the first partial sum, right? First partial sum is just x, or I'm sorry, it's just 1. Then comes 1 plus x. Then comes 1 plus x squared. And I want you to notice here that it's starting to hug this curve. Let's add in the x cubed. Add in the x to the 4th. I don't remember. There's the x to the 5th. There's the x to the 6th. Again, look at this. I'm all the way out here and here. These curves are right on top of each other. They're just starting to pull away from each other right in here. But again, notice, I know this is only going to converge is if the absolute value of x is between or is less than 1. In other words, this polynomial is only going to work for this function. It's only going to mimic this function between -1 and 1. And we see that very clearly happening. I think that's what, to the 6th or something. So because I have literally nothing else to do in my life, I graphed the 26th partial sum. And you can see here that it very closely mimics this function. Right? The more terms you add, the more closely this polynomial will mimic this function. Now, you might be thinking, why in the heck would somebody want to do that? And the answer is, back in the day, they didn't have graphing calculators, and polynomials are really easy to work with. Rational functions are not so easy to work with. So the deal here is, if you can replace a rational function with a polynomial that behaves just like it, your life gets a lot easier because you can just use the polynomial to do approximations with. Okay, so this is kind of the whole thing that this unit is about, and that is this power series. Okay, we'll talk more about this centering here in a little bit, but you'll notice that your interval of convergence went -1 to 1, which is centered at 0. All of the series we do at first are going to be centered at 0. This looks really freaking confusing, but look what this is. It's an infinitely long polynomial. So these c's are just coefficients, and it's saying I'm going to have a constant term, I'm going to have an x term, I'm going to have an x squared term. I think the hardest part about this is it's literally written in the exact opposite way they teach you to write a polynomial in Algebra 2. They teach you that a standard form polynomial starts at the highest exponent and goes down, and then in calculus we do it the opposite way when we build them. But literally all a power series is a series that contains powers of x. Okay. A power series is always going to converge at its center. And again, we'll talk more about this as we move forward. Outside of the center, there's 3 options. It's either going to converge on some finite interval, like what just happened. It could converge for all x, like it doesn't matter what x is, this is going to converge no matter what. Or it could say this thing is going to diverge everywhere but 0, so it's useless. So those are our 3 options. These are the 2 actually that we're hoping for. This is a good one if it converges for all values of x. And I'll show you some cool series like that. Okay, so I want you to try some geometrics today, deciding if they converge or diverge. And then once you do that, we'll talk more about intervals of convergence. See you later.